Okay, so how is everyone today? Good? All right. So last time we were talking about what? Area between curves?
Yes.
So we'll talk about that a little more and then move on to a new topic, but first a couple of announcements. Let's see, today's the 19th. It's come to my attention that we have an exam next week. What day is it? Is it Thursday? Is that right? It does?
Yeah.
It's not the 26th. It's the 19th today. Wait a second, are you sure? Good. Because it came as a surprise to me, and then the other students seemed to think it was Tuesday. So what day is it? Let's double check. Well, I mean, we've got to go with whatever the syllabus says. You know, people made plans.
Oh, I know.
Wait, I'm confused. What's going on?
About plans? Oh, wait, I can't really get it very easily on my phone here. Does anyone have a, and I don't have a copy, obviously you don't have a copy of it with me.
I have syllabus with me.
6:25.
Well, that's the Monday.
It says right here, 6:25 midterm exam Thursday.
Ah,
Is that
okay.
correct?
So Monday, the 25th, so it's on Thursday. Okay, good. That's even better. Better, good. All right. I was confused about the plan. It's a good thing y'all said something. Otherwise, I was gonna come in ready to roll on Tuesday. Everybody has a heart attack, including me.
I'm old enough to do that.
All right, let's get it all squared away. Okay, so a couple things need to be fixed up. So we've just turned in that, and I didn't get a chance to post 06 and 07, the pair that comes after that. As a result, we're going to make these due on Tuesday. Got some excitement about that. So these are due Tuesday. Tuesday the 26th. So that's the first announcement. The second announcement is that we have midterm. It's going to be on Thursday. As an H. Thursday, the what? 28th? It's going to be during lecture, in lecture.
Is that the only thing you're doing that day?
Yeah. So that is to say that you come in and take an exam. Okay, so to be clear, what that means is that, you know, it's going to be like a quiz. It's going to have a bubble thingy on the front. And you got to do that. And then after that, there's going to be probably about 5 new exercises. That is to say, exercises that, well, what am I trying to say? Like every one of these is a new exercise.
So that's stuff we've already gone over in the past.
Yeah, but these 5 new ones on the midterm, these ones I try to hold to a single idea. Like there's just one, for the most part, just
Right,
one
it's gonna
thing.
be
These 5 can
spread out.
can have more than one idea. On the, what I mean is like each, you know? Like each one of those is trying to test a single concept, for the most part.
So one question could test multiple ones.
Right.
Um,
So like, so, you know, in the teaching lingo, such requests are synthesis requests, where I've taught you individual components and now I'm checking to see whether or not you can put them together. So there'll be about 5 new exercises. And then beyond that, there will be the optional / redo section. So because of this, as it happens, that means that that the optional / redo section is going to cover WEX, so up to and including WEX 05 star, so the ones that are sitting right here. So what that means is that for each one of these series, 2 of them were graded out of 10, 2 were, at least 2. So I think this represents 10 exercises. Exercises which were graded out of 10. The redo section will be, so the redo section will have 1 exercise for each of these. A new exercise for each. You can choose up to 5 of these for redo. So what that means is that you can go through it. It'll say beyond here is the redo section, and then for each exercise, there'll be a little thingy that's obvious that says like do this or circle this or whatever if you want this to be graded, and you're allowed to submit up to 5 for being regraded. So you can submit 0 if you were so inclined to do that. But these first 5 are not optional. These are mandatory. Well, they're mandatory in the sense that anything's mandatory, right? You could just leave, I guess. But that means that these are 50 new points, because these are going to be graded out of 10. And conceivably, you could turn 0 out of 50 points into 50 out of 50 points on the redo section.
I thought we were going to get to be able to do all of them, but I heard, I might be wrong, but I thought I heard you say we would have the option to redo any of them.
No, you can redo any of the out of 10 ones, but you can only select up to 5. Because in the end, the reason why it's not all of them is because and I'm sure I didn't say all of them, unless it was just like a gross mistake on my part, because I wouldn't allow it to be all of them because I've historically tried that, and in the first place, it's too much labor, and in the second place, students, and even more importantly, students take the bad strategy of saying, I'm going to show up for the first time on the midterm, and they die. Not really, but they don't make it. They don't succeed. So as a result, that can't be the policy. All right, so you can choose up to 5. And it might come to pass that you say, yeah, I'm going to try out that one, and then you start doing it, and then you realize, no, I don't want that to be one. You can say, no, not this one. But the thing is that if you submit a redo for grading, then that will be your grade. So conceivably, your grade could go down, right? That's not the point, but I mean, obviously the point is for y'all to say, oh yeah, it would be best if I studied those specific exercises, and then you study those hard, and then you significantly improve your standing on the redos. That's the point. But the reason why because I used to I had tried one where you can have the better of the two, and then it wasn't going very well, and I find that this policy causes you to have some skin in the game. So, you know, I'm just trying to turn the knobs.
So you're not gonna pick the one with the highest score?
No, whichever one is last. So like if you, so you know, maybe it's the case that you got a 8 out of 10 and you just think, oh man, if I just had 10 out of 10, I'd have 100 in the class. You know, maybe, you know, who knows? Maybe you're in that good of a position, and then you redo it and you get a 7 out of 10. Well, now you have a 7. Okay. But you know, if you get a 10 out of 10, then you have a 10. Good. Any questions?
So the 5 new exercises, is that only going to be through WIS 05?
Yeah, it's going to cover that same.
Up to WIS 01?
Yeah.
Just want to make sure.
So we just turned it.
Right. This right here. That one right there. Yeah. Good. Other questions?
Are there any WISs due on that Thursday?
This one?
Yeah. Oh, well,
This
that's
one?
due on Tuesday,
Yeah, that's
so-
Tuesday. This is Thursday.
So Thursday, we're going to have WISs due on Thursday?
Yeah, we're going to have to, otherwise we're going to get behind. But we can't quiz that day because we're examining
So
that
6
that
and
day.
7 are due on Tuesday? Right. 6 is due Tuesday and 7 is due Thursday, or 6?
No, they're both going to be due Tuesday.
Okay.
And then, so 6 and 7 was last week.
Okay.
And then 3, this week, like for example, the lecture that we're presently in is 8. So we'll make WEX 08 and WEX 09 due Thursday. So you come in, turn in some stuff, take an exam. It'll be party. Summer school, it doesn't sound like a good idea. It's too much, it's too fast. But it is what it is. Other questions?
We want to use
A ruler?
Yeah.
By all means, as long as it doesn't have like, you know, the fundamental theorem of calculus on it or something. Yeah, it's fine. Okay, so good. So let's talk a little bit more about area and stuff like that before we move on to a new chapter in the book. All right, so good. To remind you of the technicalities here about the integral, is that if we have, so given an f on an interval a to b such that this function is greater or equal to 0, the picture is this same picture that I've drawn so many times. Then this shaded area is the integral. So integral a to b of f of x dx is this area. In particular, it is the numeric value of the area. So like if that happens to be, say, you know, 1.5 square inches, then the answer is 1.5. The integral is 1.5. All right? And then colloquially speaking, this is it is very often heard that you say that this is the area under the curve. Now, I put scare quotes around under because that's a little bit, in my opinion, it's a little bit clumsy of a word because you can lose track of the following. So the under remains unconfusing as long as this condition is true, as long as the function is greater or equal to 0. But if the function can never be less or equal to 0, then the under thing is can be a little confusing. So in particular, given f on a to b, and then I'm not going to include that condition, so without that condition, then we could have a picture that looks like this. So now, you don't really, the phrase area under the curve is not as great, in my opinion, because now the region that the integral is referring to, it's referring to this, and also this, and also this. So it's not really the area under the curve. What it really more possibly is the area between the x-axis and the curve. There's even more intrigue to it, and that is that you can see that there's kind of like 3 different pieces to this area. The integral from a to b of f of x dx will, I'll put it in scare quotes here, sees these as positive area this I just put scare quotes around it just because obviously the integral doesn't see anything. Sees these ones. Oops, these ones. So the ones above the x-axis are positive. They're seen as positive. Whereas the one below the axis is seen as a negative area. So, as a different exercise, suppose that we have one of those find the area of the shaded region exercises. Okay, suppose that we're considering that, and that the region, after some consideration, looks like this. I'm just redrawing that same one that's up there. Well, the meaning of this language, find the area of the shaded region, that means that each one of those three pieces, we want to consider them to be positive, right? That this one has a positive area, and that one has a positive area, and that one has a positive area. That's conceptually what that language is saying. So as a result, can we use the integral? Will the integral, will this right there answer this question? It won't. It won't because what we want is we want to consider each one of those pieces as being positive. But the integral, just the straightforward integral, all that it does is just, it counts such things as positive, such things as negative. So we can't use the integral well, first let me explain what this says. So that means we want all pieces to have positive area. That's what we want. So we can't use this. Well, because that middle piece will have a negative area. Yeah?
So you say the area won't change no matter where is it. So even though it's at the bottom,
Mhm.
the area will be the same one. So the area will not change no matter what. So
Okay, there's a different question. Okay? So here, how do I explain it? All right. It's a fair question. I need, what do I need? All right. So here's a sheet of paper. And for the sake of argument, I want you to ignore that bit. Okay? Just so it would be the case that both sides look the same. So just ignore that. Now, I'm going to put a red arrow going this way, and I'm going to call this arrow number 1. And then I'm going to put a green arrow going this way, and call this arrow number 2. Okay, and then I'm going to turn this into just a little rectangle here. And the rule is that first you follow arrow number 1 and then arrow number 2. And what this does is it creates a swirl pattern. So it's an area that looks like that. So first red, then green. So it's swirling counterclockwise. All right. And now what I'm doing is I'm tracing the same thing. So, but I've turned over the page. In particular, I flipped it. So there's the red one. There's the green one. And then I continue this like so. And now, with the same rule, you follow 1 and then 2. So now the swirl looks like this. And is that clockwise or counterclockwise? That's clockwise, right? That's the same direction as the clock. Whereas this one is opposite. Okay, this one, that if your fingers are pointy, that one agrees with your right hand. That one doesn't agree with your right hand. Okay? So, now, if we ignore the arrows for a moment and the swirl, and I take this and I move it around, like so, and like this, and like this, then the area is the same, right? That doesn't change the area, that doesn't change the area, that doesn't change the area. So that's still true. Notice that none of these things that I'm doing change the swirliness either, right? Still swirling, even if I do this, right? Still swirling counterclockwise. Still agrees with your right hand. Okay, But so now, this one, the size of the area is the same, right? But notice that the swirliness has changed. Now it agrees with my left hand instead of my right. So what I'm telling you is that the things that are permissible are if I can't pick up the sheet, if I can only do this. If I can twist it, but not pick it up. Move it up and down, that's fine. But if I'm allowed to pick it up and do that, then that negates the area. So what I'm telling you is that the thing going beneath the axis is like that. It's that kind of idea. Fine. So we can't use this because the middle piece you know, that one right there would be counted / seen as negative. Okay, so we can't use the integral directly. But one thing we can do is, and one thing that we did do last time, is that we could do the following. We can find the zeros. So in the picture, visually, how many zeros are there? 2, and there are these places, right? Right there. So let's say that we find these zeros, and the way that you do it is you say, well, this is y is f of x, and what's the equation of the x-axis? Y equals 0. So we say that those two conditions must be true. It must be the case that y is f of x and y is also 0. So then we solve. F of x equal to 0. Again, because of the picture, our expectation is that there should be two solutions. Suppose we solve it. And that we determine the solutions are C1 and C2. Then we could do the following. We could say, okay, well, let's integrate just between consecutive lines. So we could integrate from there to there, and we could integrate from there to there, and we could integrate from there to there. Now the thing is that when we perform this first integral, where the question of making it to where all of the areas are seen as positive, then the integration here is correct already because it's already positive. And similarly, in the last region from C2 to B, the integral will give the correct answer. Now, that's for where you want to see all of the areas as being positive. Now, will the integral from C1 to C2 give the correct answer? No, but it will be. But how will it be wrong? It's the negation of the right answer, right? So then, if you integrate from C1 to C2 and you get -5, then the real answer is 5. Okay. So then, the way to answer the question, we could do the following. We could say, okay, we'll integrate from A to C1 of f of x dx. Just leave that there for a second. And we'll perform another integral. We'll integrate from C1 to C2 And then once we've done that, we'll put that on pause and then integrate one more time from C2 to B. Of f of x dx. And just reminding you about the score is that this one was right, that one was right, and this one was wrong, but the only thing wrong with it is that it was the negation of the right answer, of the correct answer. So then the real answer is that it'll be that one, and then subtract that one, and then add that one. Okay, so any question about this idea?
For the middle one, can you like do the absolute value?
If you, well, so I make no dispute. I'm going to go on and talk some more about that. But here's the thing. If you're going to evaluate this with the fundamental theorem, the fundamental theorem doesn't have any absolute value. The antiderivatives that we know don't have any absolute values in them. So in a sense, going from here to absolute value is like stepping in the wrong direction towards the end of the problem. But I agree entirely that it can be understood as absolute value. Okay, in fact, that's what I'm going to say right now. So alternatively, we could flip the middle region over the x-axis and then the result would be entirely above the x-axis. So that is to say that the ones that were above, we'll just leave them because they were fine. So that one was fine, and that one was fine. So we're leaving those. But as for that middle one, we're going to take it and flip it over the x-axis so that the result looks something like that. So now, that one up there is f of x. Y is f of x. Is this one also y is f of x? No, what I mean is that the whole red piece. So like this red up here is y is f of x. What about this red?
Absolute value.
Right. This is y is absolute value of f of x. So this idea of flipping the middle region, but in fact all such regions that are under there, flipping them up, this is you know, algebraically by using absolute value. So as a result, we could just integrate this. Now, that would give us the right answer, the correct answer. So therefore, the integral from a to b of absolute value of f of x dx is the area of the shaded region. And of course, this means where all pieces are have a positive area. But the thing is that, well, if you want to use the fundamental theorem of calculus, you can't use, you know, none of the rules have absolute value in them. So in the end, you have to do this. right? So what I'm saying is that I'm trying to, for anyone that didn't make the connection between these two ideas is exactly this, is that, you know, in order to do this, in order to evaluate this, with the FTC, you do exactly this. Okay. Any question about the ideas? So now, that being said, what I'm telling you, well, among the things that I'm telling you, is let's draw one last real big picture version of that. This is not something that is going to be tested. Rather, I hope it will give you a good intuitive explanation of what's happening. Here's just a bigger version of it. So what I'm telling you, remember that the definition of integral, what you do, is that you break something into rectangles, right? So, you know, this is the x direction, the first direction, and that's the y direction, the second direction. And what we do to break it into rectangles is we say, okay, we'll cut up the x-axis. The x-axis is always, the pieces always look like this. So that's a little x-axis piece. And then if we want to find a rectangle that fits up there, then that means that now, because the graph is up there, we go that way. So now we go this way. Maybe we'll use this rectangle. This is just one of many rectangles. And now, that particular rectangle, how's it swirling? Does it have a right-handed swirl, a counterclockwise swirl, or which one? Counterclockwise, right? So that agrees with your right hand. First red, then green, so like that, right? So this is positive. And then if we do a similar thing with this one, so the x pieces are always in agreement with this one. But now from here, to get to the function, do we go up or down? We go down to make a rectangle. And the rule is still the same. You follow the first piece first, and then the second piece second. So that now it looks like this. Well, do you see that that one is a left-handed piece? Or if you like, a negative piece. So here's the last bit. If we take this and then we flip it up, the result will be a rectangle that has positive orientation. Orientation is the math word. I'm trying not to say it. Yeah?
So basically, we're going to start with the right to go to the left. It's doing the opposite.
Right. Correct. So, yeah, these ones are considered positive, and these ones negative. That's just a completely arbitrary convention, right? It's just one or the other. We just happen to say positive or negative. But it has something to do with the bias of, 90% of everyone is right-handed. But, DNA is a helical structure, and it has according to our convention, it has a negative spin. So DNA is left-handed. Ha. All right. So let's do one last one of these, and then we'll. Oh wait. Well, I want to make one more comment. It's a similar kind of story. when it's like this. So when it's, you know, like when someone is really good with their hands, you know, like, you know, some people are just like real good with their hands. Like I'd say like, you know, like a plastic surgeon's probably good with their hands. But, you know, some people less so. Such folks are called dexterous. That means, you know, you've got high dexterity. And you know that dexter means right-handed. And if you're ambidextrous, that literally means two right hands. You can you can use both hands. That's what ambidextrous means. And do you know what the word for left is? Sinister. And that's because left-handed people historically were considered, you know, like evil. Yeah. Yeah. Anyway, sorry, I'll stop. I'll get off my soapbox here. So when the problem is find the area of the bounded region bounded by, and then it goes on, you know, goes on to list something, you know, like something like this: x is a, x is b, y is f of x, y is g of x, and you know, if it turns out that the picture looks like this, so if that's you know, if this one is A and this one is B, the red one is f of x, and maybe g of x does something like this. So can you see the shape that we're referring to? So see if you can see it with your mind's eye there. If you need a hint, it has, I would say, I think most people would agree that it has 4 distinct pieces. All right, so it's going to look something like this. So that's the area. Now, that particular shape, that shape right there, the integral from A to B of f of x minus g of x that is related to this picture. But again, some of the regions the integral will see as being negative, and other regions it will see as being positive. So we'll see, again in quotes, these as positive. So I need to, you know, from the word these, I need to point at the thing. It says which ones are positive. So which regions are going to be positive according to this integral? Which pieces? Oh, sorry, I didn't follow.
That one
This one?
and then the last
And the last one? Okay. Why does this integral see that one as positive? Well, yeah, in the end, because red is higher than green. In the end is the reason. So, so in particular, it'll see these. So that one there, and that one as positive. And the others it will see as negative. Whoops, as negative. The integral a to b and now g of x minus f of x. So what's its story? Right. So is the opposite. So to make just a little quick one. So now, in particular, this one we'll see that one as positive because green is on top, and that one is positive, and the others is negative. All right. So what if, you know, the problem that we're talking about is find the area of the bounded region, which is to say those four pieces, we want them all to be reckoned as positive. Well, you could use two different integrals, right? You could use that integral for the second and fourth region, and you could use that integral for the first and third region, right? You could do it that way and say, well, for this one, not exactly these limits. I mean, I just mean integrating the function g of x minus f of x. Okay, what integral will give us the correct answer, which is to say it sees all of the regions as positive? Absolute value. The integral from a to b of absolute value of f of x minus g of x dx, which is going to be the same as if we were to do it the other way, but and still with absolute value. So it doesn't matter. The integral sees all regions as positive. All pieces as positive. So if our desire is to perform an integration such that all pieces are seen positively, well, we can't use this, not directly if we want to use the fundamental theorem, because fundamental theorem doesn't have any antiderivatives that have absolute value in it, but we can endeavor to cut the region into pieces like the following. We could find the intersections of y is f of x and y is g of x. So on the picture here, oh, whoops. Okay, so then find the intersections. Now, in a real problem, I'm not going to give you a plot. You're going to have to make the sketch. You're going to make some manner of sketch, usually. So that means that somehow you're going to have to perform some math to do this. So what math is it that you need to do to do this? Find the intersection of y is f of x and y is g of x. That won't. That's not it, because if y equal to 0 is down here, then the red never touches down here, and neither does the green. Yeah, that one, right? Because what we want is we want to find inputs x such that the outputs are the same, right? So then we do this. By solving the equation f of x equal g of x. Now, according to the picture, what is your expectation about the number of solutions? Okay, so I heard 4 and 3. 3? Okay, what makes you say 3? Right, because, well, the main idea that, one of the things we want to really, math instructors want to really hammer home is that the solutions to equations correspond to the intersections of graphs. So the fact that you can see 1, 2, 3 intersections means that you should expect there to be 3 solutions. All right, do this by solving. So we expect one solution per intersection. All right, so then suppose that we've done that, and we find these, and suppose that we call them C1, C2, and C3. And we still want this shaded area, which is to say that we want to find the area such that all pieces are considered positive, having a positive area. That means that we can do the following. Therefore, we can say the absolute value, a to b, the integral from a to b of absolute value of f of x minus g of x the way that we can do it is, well, we can proceed by dropping the absolute value. But that will require us to break this integral into how many pieces? 4, 1 for each region. So it will be 4 integrals, all added together. So integral, something goes in there, dx, plus, of course, this isn't an integral until I add the limits, right? So, what are going to be the limits of the first integral? A to C1, and then C1 to C2, and then C2 to C3, and then C3 to B. So is there any question about why 4 integrals, or why these limits? Finally, in order to make it to where we've always selected, we're selecting the thing that's going to yield the positive result, what are we integrating in the first integral? Okay, so I heard g minus f, and then I thought I heard you start to say f minus g. So which one is it? Eventually, but for this specific one right here. Well, okay, so for this one, why g minus f? For this one. Ignoring these, just this one. Yeah? Because g's on top in that region, right? So green is higher than red, in the end, is the reason for that specific one. All right, so this one will be g of x minus f of x. Are there any others that'll be that way? Yeah, right? The first one is that way, and also the third one, right? So this one will also be g minus f. How about the others? How about the second and fourth one? F minus g. Okay. Any questions about this concept? So I recovered this ground because, well, I got some feedback from y'all that it wasn't exactly clear. So let's do one more of these, and then we'll move on to a new idea. One more example. So please find the area, find no, I want to say it like this. Let R be the bounded region bounded by x equal -1, x equal +1, y equal exponential of x, and y equal 3 minus the exponential of x. First request, sketch R. Second request, find the area of R. All right. So, well, you've got to know some things in order to answer this question. So let's just quickly review what it is that you need to know. So by now, surely, we're all clear that x equal to 1 and x equal -1 and x equal +1 are vertical lines at x is -1 and x is 1 respectively. Then you've got to know, well, what do these look like? What does that one and that one look like? Well, so let's write that down. So I'm going to draw 3. The middle one is not part of this problem. It's just to help me explain something. So y equal exponential x, that's just something that you're required to know. So, well, what is, if x is 0, then what's y? 1. Okay, good. So then that point is on it, right there at 1. And then from here it goes up quite rapidly, in fact. And then from here it dies down, and that's an asymptote. It keeps going that way, gets closer and closer to 0. All right, good. Now, this is not, this one in the middle I'm going to do is not part of the exercise, but it's just a stepping stone to understanding something. What happens if I take exactly that red, but I negate e to x? Then what's the effect? Very good. So then it'll be just like that one, except down. So like that. And then, the reason why I did that one is because this one, the one that we're actually interested in, is the same as this one, except you add 3 to it. Right? So then, writing this as y is 3 minus e to x, or, if you like, y is negative e to x plus 3. It's the same. The effect is going to be to take this one here and then shift it up 3 units. So that means that if this is 1, 2, 3 right there, that means that there's an asymptote on the left anyway, right there. When you plug in 0, x is 0, what do you get for y?
Question, why is it 3 and why not 2?
Y is what 3?
The asymptote. If you shift it up 3 and it's negative 1, it should be 2.
Well, let's think about it for a second. So do we agree that that e to x can get as small as possible? Right? So meaning, what I mean is as near to 0 as possible. So that means that that can get as near to 0 as possible, right? Which means that this expression can get as close to 3 as you like it to be. Not just 2. So,
I'm just confused.
yeah?
Oh, okay, gotcha. So you're adding 3 to e to the x.
Yeah.
Gotcha.
Yeah. But one thing that will be 2 is that, notice that if you plug in x is 0, then that'd be 3 minus 1, which is 2. So right here like this. And then it'll be just like this one, so from here down, and then from here to the asymptote. Okay, so these are the things that you've got to know before you get here, before you get to this exercise. All right? So to make a sketch then, we want to have a sketch that includes all of that. So we've got, well, here's the x-axis, y-axis, one, 2, 3. I'm going to draw this dashed line to help me. So that's y is 3. The red, the e to x does this. So it goes through that point there. And then from there it goes up quickly. And then this way towards its asymptote. So this one is y is exponential of x. The green one goes through where? On the y-axis. Goes through 2, so it's right here. From here it goes down. And from here it goes to its asymptote. Now, R is the bounded region, so the exponential bits are sort of like the interesting part. But, you know, there's another part, and that is it has to be bounded by x is -1 and x is 1. Now, where approximately is x is, do I draw x is -1? So where will that be? To the left, right, of the origin, right? So it'll be, you know, like here-ish. Now here's the thing that you need to be worried about, or not worried necessarily, but paying attention to with the sketch, is that this is just a sketch, okay? So if I put x is -1 there, then, you know, if it were a perfect plot, right, if I was getting like out a microscope, you know, and doing it, then 1 should be exactly that far, but on the other side. But it's just a sketch. And the thing that we need to worry about is that, notice that intersection right there. We need to know, in fact, should x equal to 1 be, you know, to the left of that intersection, or should it be to the right? You know? Where will it be? So, to the left of the intersection? Of y is the exponential of x, and y is 3 minus the exponential of x, or to the right. Now, sort of to make this an interesting exercise, probably on the right. Why probably on the right? From the point of view of wanting this to be an interesting exercise. Yeah, you know, we'll have, that means that some of the time green will be on top and some of the time red will be on the top. But it could conceivably come to pass that, you know, it's like that, so that green is always on top. That could happen. But probably more likely is like this, so that sometimes it's one way and sometimes it's the other way. But at any rate, how do we figure it out? How do we figure out what the case is? Right. So therefore, we need to solve exponential of x equal 3 minus exponential of x. Because that'll tell us where that x occurs, and then that'll tell us whether or not 1 is more or less than that x. All right? So now how do we solve this equation? We do. We've got to get to x all by itself. It does not. So I think probably, can we agree that we could, it's possible to add exponential of x to both sides? And so if we add if we do that on both sides, the new right-hand side is 3, and what's the new left-hand side? Right, twice exponential of x. Okay, now what? Divide by 2. So exponential of x is 3/2. And now, yes. So it's just like this 2, that 2 right there, from here to here, that 2 changed sides. But really it was not just the 2, but 2 and its operation, right? So this was a 2 with a multiply, changed sides to the other side to become a 2 with a divide. So now we want the exponential to change sides. And when it changes sides, just like multiply by 2 becomes divide by 2, exponential becomes a logarithm. Which is to say that if we want x to stay on its side, and if we want 3/2 to stay on its side, and we want that to change sides, when it changes sides as logarithm. So, log. An alternative way to see that visually is to recall that another way to write exponential of x is as exp of x, so that equation looks like exp of x is 3/2. So if you want to solve for x, then the x stays on its side, the 3/2 stays on its side, and when the exp moves to the other side, it becomes log. Okay, so we did this. We figured out that x because we wanted to know where that intersection was, right? So in the end, we wanted to know where that intersection was because we wanted to know, relatively speaking, where that 1 is. So how does this tell us? Okay, so evidently the x is log of 3/2. So is it more or less than 1 or what? We don't know. Well, let's think for a second. I call this log because that's what it is in my math head. But other folks are going to call it natural log, or if you like, logarithm with what base? The natural base, right? What is the natural number? No. 2.71 blah blah e, right? The natural number. This is the logarithm in the natural base, e. The log that humans use, at least historically most often, is log base 10, for no other reason than the fact that we have 10 fingers, by the way. There's no other reason than that. If it had come to pass that we had 8 fingers, I guarantee we would count in base 8. But I lost track. Yeah, so the natural number is about 2.7. And 3/2 is 1.5. So the fact that 1.5 is less than the natural number e, 1.5 is less than 2.7, that means that the logarithm of 1.5 should be less than 1. Right? So what I'm telling you is that even without a calculator, you should have an expectation about how big this number is. So let's verify that.
So does n equal e?
No. Logarithm is natural log is the logarithm that has the base, which is the natural number, e. So it's not that they're related, like this, or if you like this. Good. Oh yeah, calculator. Log of 3/2. Nope, 3/2. Y'all see that? So 0.4-ish. So 0.405. So that tells us that this right here is x is the log of 3/2, and that x equal to 1 must be a little bit further than that. So x equal to 1 is about right here. Okay, so now the plot is a little bit busy there, so could you please sketch the area? Because there's a lot of lines there. Some of them are just there to help us understand what's going on, but you need to be able to figure out what area is it that we're talking about. So When you have it right, I think we could probably agree that it's got two pieces, two main bits. So one of them is going to look like this. That's one of the pieces. And if I were grading this, if I had submitted this as an exercise to y'all, and y'all were grading, I would expect some of you to draw this, something like this. So is that right? Why not? I mean, I stopped at the 3, real careful, right? Remember that y = 3 is just there to help you draw the green, right? So then, in fact, it needs to continue past it. So like this, and like this. And if it were a perfect drawing, that'd be symmetric, but, you know, it's a sketch. Any question about this shape? Okay, so that's the answer to part 1. The answer to part 2 is that, well, because we want the area of the shaded region, that means that we want all regions to be reckoned as positive, which means that we can integrate from -1 to 1, and the thing that we can integrate is absolute value of one of them minus the other one. So I'll do this. I'll say that it's the red one, e to x, and then minus the green one, minus 3 minus e to x. And now I'm going to wait. Well, I put it in an absolute value, so it shouldn't matter. Yet. There's something that's not right.
Yeah, because there's a parenthesis, so you have to distribute the negative 12.
Right. Remember, it's the green one, or no, the way I'm writing it is I'm doing the red one minus the green one, right? Now, so what we mean is the red one minus, and then all the things that I'm covering up, right? So at the present time, notice that the way it's written, I'm only subtracting the 3. You can't only subtract part of it. You got to subtract all of it. So as a result, what I'm telling you is that when you substitute things in, it's a very good idea to put parentheses around the things that you're substituting in. So notice, here's this red thing. If I put these parentheses around the red one, those parentheses actually don't affect anything. It so happens that adding or removing those parentheses has no effect. But these parentheses around the green thing, they make it right. So notice that when we distribute the subtraction, as y'all said, we'll eventually be adding that term.
But is it not, you have the absolute value,
I'm sorry?
but you have the absolute value, so.
It still matters. Because if these parentheses weren't around the green, then the thing inside of the absolute value would be -3. The e to x's would cancel. They'd be gone. Okay. Good. So any question about that? In the end, the whole point I'm trying to make is that when you substitute stuff in, it's a good idea to, you know, put parentheses around it. Students want to, I suspect, not just students, but just humans generally, don't want to, because we're lazy, we don't want to put the parentheses because sometimes you don't need to do it. So because some of the times you don't need to do it, people want to never do it. You know, if you're not sure what I'm talking about, you should look up something called a Skinner box and get depressed. Whatever. So then, simplifying this a little bit, the integral from 1 to 1, keeping absolute value for the moment, that'd be 2 exponential of x minus 3, like so. So that's just performing a quick algebraic simplification. And then we'll need to break this integral into pieces. How many pieces? 2. Why 2? Right. Because there's kind of like the stuff that's to the left of that intersection and the stuff that's to the right of that intersection. So like that bit and that bit. Okay, so that means that we'll want to integrate from -1 to what? Yeah, log of 3/2. And then, all right, we're going to integrate something there. And then plus the integral from log of 3/2 to 1. I'm going to integrate something else there. And the question is what goes in where? What about this one? Okay. Why?
Because that's the equation. We don't put the absolute value.
Okay, what goes in here? In the end, yeah. This one needs to be red minus green. Right, so can we agree with that? That this one I'm pointing to is red minus green? And this one would have to be the other way, green minus red? So because this one is green minus red, and because here I have it written as red minus green, so then what goes here? If that's bothering you, if that's disturbing you, you can skip this intermediate step. If I think maybe this intermediate algebraic step is bothering you. So I'm going to ignore it for a moment. So for this one right here, it needs to be green minus red. So it'll look like 3 minus exponential of x, that's the green one, and then minus the red one. And then the other one will be the other way around. The red one minus the green one. So like that. Good. So then now we can algebraically simplify both of those and get the following. So it'll be integral from -1 to log 3/2. And then that would become 3 minus twice exponential x dx, and then the other one would be integral from log of 3/2 to 1 of twice exponential x minus 3 dx. Any question about getting to here? So, if this question, so in the first place, we haven't answered the question yet, not, at least not completely, but getting to this place is worth like 8 out of 10 points. So like actually doing the rest of it is like the boring part. If I want to test you just doing the fundamental theorem of calculus, and that's specifically what I want to test, then I'll give you a question that starts here, right? But this question is primarily about you getting to here. So any question getting to here? Because the rest of it I'm just going to just race through because it's boring. All right? So evaluating this. So we want to use the fundamental theorem, which is to say that do we know an antiderivative? So do we know the antiderivative of 3dx? Yeah, that is a constant multiplier, and antiderivative is homogeneous, so it goes away. Do we know the antiderivative of x dx? Yeah. So as a result, we can proceed immediately with the fundamental theorem. This would be 3 times x minus twice exponential of x, evaluated from -1 to log 3/2. Because, well, remember that exponential is the neat function, the function that happens to be its own derivative and its own antiderivative. Similarly, the next one would be twice exponential of x minus 3x. This evaluated from log 3/2 to 1. All right? So now we've got ugly calculator thing. On a question like this, where the arithmetic ends up looking like this, the way I would phrase the request is I'd say, please give me the exact answer and also an approximate answer to 3 places past the decimal. That's more or less what I'd say. So to get the exact answer, we want to plug in that. So 3 log 3/2 minus twice exponential of the log of 3/2. So that's plugging in at that point, and then minus 3 multiplied by -1 minus 2 multiplied by the exponential of -1, like so. So that's the first thing. The second one would be twice exponential of 1 minus 3 times 1, and then minus twice the exponential of the logarithm of 3/2 minus 3 times the logarithm of 3/2. All right, so I see that fearsome looking thing there. The exponential of the logarithm of 3/2. What's that? I claim you can answer it right here and now without a calculator. It's 3/2. Right, because the exponential machine, the exponential function, and the logarithm function are inverse functions, which is to say that if you lined them up, logarithm is occurring first. So if we have a logarithm here, so we're going to give input to that machine there, and then we wire up, you know, immediately after it, the exponential machine. What I'm telling you is that the process ends up looking like this. Suppose that we put, you know, a cat in there. That's my artist's impression of a cat. We put that in there, and then out comes, at least in the intermediate step, logarithm of cat. And now we give that as the input to the exponential machine. And then, so what comes out is, on the one hand, it's, you know, exponential of the logarithm of the cat. But that's just the cat. So really, that's a complicated conveyor belt. So exponential of the logarithm of 3/2 is just 3/2. So this would be like this. So that one has to stay. So 3 times the logarithm of 3/2 minus 2 multiplied by 3/2, and then subtract 3, and then add twice the exponential of -1. And then for the second set of square parentheses, that's twice the exponential of 1, and then minus 3, minus 2, that silly thing again, 2 times 3/2, and then plus 3 logarithm 3/2. All right, so now 2 times 3/2, the 2's cancel. Good. Oh, wait, I made a mistake. Where's the mistake? Can you see it? Let's leave it. I made a mistake. Let's leave it. But I'll say here and now there's a mistake. So let's find it. Let's see what happens if we continue. So then this would be, these 2's cancel, and then that would be subtract 3 more. So I'll simplify this just a little bit. So this would be 3 logarithm 3/2, and then those 2's cancel, so that's minus 3, so that's 6, minus 6, and then plus twice exponential of -1.
Supposed to be minus, right?
I don't know. Maybe. There's a mistake somewhere. So then this is minus 3 and then minus 3 more, so that'd be minus 6. Minus 6, and then plus 3 times the log of 3/2, like so. And so now I'll combine stuff. I see that we have 3 log 3/2 and another 3 log 3/2, so that'd be 6 log 3/2. Then I see that we have subtract 6 and subtract 6 more, so that would be minus 12. And then I see that we have plus twice exponential of -1 plus twice exponential of 1. And again, there's an arithmetic mistake here. But supposing that I hadn't noticed that yet, this would be my alleged exact answer, and then to find the answer to several places past the decimal, I need to put it in the calculator. All right? So this would be, so to type that monstrosity into the calculator, it would be 6, and then multiply log 3 divide 2, subtract 12, plus 2 multiply, and then if you press the shift button, and then the log button, that gives you the exponential button. That would be twice exponential -1 plus twice exponential of 1. Okay, so I'm going to type that in. 6 times log 3/2 minus 12 plus 2 times the exponential of -1 plus 2 times the exponential of 1. Okay, so typing that red thing into the calculator there, my calculator is saying that number there. So it's saying negative 3.395. Rounded to 3 places past the decimal. Now I claim that at this point you should say, oh no, this could not possibly be right. Why could this not conceivably be right? Right, because we worked so hard in our analysis to make sure that we were arranging matters so that the integral would view all the different pieces as being positive. And if you add up a bunch of positive bits, you got to get a positive answer, right? So can you see that that this is a nonsense answer? This is nonsense. So now, I did say, and I did mean that if you get to here, that's like 8 out of 10 points. But if you were to come all the way down here and just leave it there and just say, -3 something something, and not explicitly say something like, this is nonsense, but I can't find my error. If you just leave it there, I'm probably going to take off a lot of credit, because leaving this answer here is, what it sort of signifies to the instructor is that you really don't understand what it was that you were trying to do. Right? It would be like if you sent it turned out there were Martians and they came and visited us, and then we said, hey, could you go to the store and get some apples so that we can eat, and then they come back and they have apples but they're plastic. Right? It's like, okay, well, I see that you kind of got the idea, but something fundamental is missing. And that's kind of what this is. That being the case, so the answer, let me say it like this, a negative answer is nonsense. All right, so then where's the problem?
Should it have been +3 instead of minus?
Yeah, right there. So specifically, I was going quick, right? So then somehow, I don't know how, but somehow I like ignored that bit that I'm covering up. At any rate, that's -3, and then we're subtracting it. So that 3 should in fact be a positive 3. So as a result, that means that you know, to make my corrections, this would need to be a positive 3, right? And then now this would be -3 and then +3. So those that's in fact not -3 minus 3 becoming that -6. It's actually -3 plus 3 becoming a 0. So this is you know, that's a correction that comes down to here and makes this a 0. And now the rest of it is okay. So let me type it back in. What? Oh, yeah, okay, you're right. Thank you. Right. Yeah, okay, as a result of this one being 0, yeah, exactly. So this one needs to become -6. Yes, thank you. Okay, so now type that into the calculator. Okay, so now fixing that that mistake, the calculator now reads that 2.605. Now, I don't claim that you should have any sense of whether or not 2.6 is reasonable in size. Like, it's not clear, I think, unless you're like real good, like thinking about that kind of thing. Should it be 2.6 or should it be like 26? I don't really know. But at least the sign, the positive or negativeness is right now. And this is the right answer. Any question about it? Yeah?
Can you show the picture again of the?
This one?
Yeah. So the part of on the right-hand side, where
Yeah.
the blue is under the x-axis.
Uh-huh.
The reason you don't have to do anything to compensate for that being below is because you're subtracting a negative value.
No, not exactly. It's the distinction is that because we're doing red minus green, do you agree that even when the green is down here, it is still the case that it's below the red?
Yeah.
Well, that means that red minus green is a positive number.
Right.
So what I'm telling you is that it's not relevant where this axis happens to be because we don't happen to be measuring relative to it. It's red and green are being measured relative to each other.
Yeah, but you're still just doing it with the integrals, right? So, like you're finding.
Let me ask you this. You look like about 6 feet. I'll just go with that. Tall. So then, what if we're in Texas? What if we went to like California? Then, in that case, you'd be thousands of miles tall, right? Because California is thousands of miles away.
Probably not.
Probably not, right? Probably 6 feet, right? So what I'm saying is that imagine that I could grab hold of this shape and also grab hold of the axis. And imagine I just grab hold of the axis and just take it away. How does that affect the area of that shape?
It doesn't, but it would affect like if you took the integral of the red one,
Uh-huh.
but you had moved the x-axis way down, that would affect that. But I mean, the difference.
But it doesn't as long as you also integrate the red one with the x-axis in the same place. See, here's the difference.
Yeah, yeah. The
Here-
relative. Yeah.
It's the relative difference between them. So like, for example, if you go out in the parking lot, and we call that the ground, you'll be 6 feet there. But now that we're on the second floor, are you like 26 feet? No, right? Because we're measuring the relative distance between your head and your feet, not.
Between the two lines.
Yeah.
If we didn't have the two lines, then the negative part would play in.
But just for this one, just to hear me, the
Yeah.
absolute math you're doing here is
In fact-
positive minus negative to get positive.
It's not positive minus negative. It's the bigger one minus the smaller one. So, for example, it could be the case that, say, the red one is at height negative 100, and the blue one is at height negative 200. So now, negative 100, the bigger one, minus negative 200 is 100.
If you're just in this case.
Here, I'll draw a picture.
I understand what you're saying.
This problem here. The question is suppose that that's the axis, that this is x, and this is y, and that the shape that is being contested is right here. That this is A, and this is B, and this is the big one, and this is the little one. So something like that. So that what we want is the area right there. So suppose that's what we want. Well, you could do it in the way that we were talking. You could do the integral of the red function minus the green function. You could do that. But another way to do it, or if you like, because the integral is additive, you could also look at it like this. You could say that it's actually equal to, I'll draw two axes. That, and then here I need to do this. Okay, so far. So I just drew two axes, but with them in separate places. So then this integral so comparing just these two, can we agree that this one is too much? Right, this one is more area than that one. Because we're counting this bit of area, and we didn't want to count it, right? That one. And then notice that this is exactly how much that we overcounted. So this one is, this area can be seen as that area minus that area. Now here's the thing, is that suppose that I grab this area and I hold the axis and I pull it down, say. Notice that this area doesn't change, but these do, right? So specifically what I mean is that, these lines go down here like this. What I'm saying is that, notice that if I were to, instead of measuring the red one relative to this one, what if I measured it relative to my other favorite one down here? Then that would add all this extra area, so our answer would be even more wrong. But as long as we measure this one also relative to the same one, then it has no effect. So what I'm saying is that you can move this one around however you want, even to the point of moving it way up here, and the whole thing is negative. Okay? Okay. Good, so now let's move to a new topic. All right. Remark. No, section. We're in a new place now. So section 8.1, I'm going to call this by parts. Now, the name of this section, according to the author, is integration by parts, but I find that to be a very poor name for what this is, so I'm just going to call it by parts. So to remind you of the overall status and situation of calculus, where we are in the course, is that, well, here's a machine. And as input, we can give it a function. And suppose that the output of that machine is another function, which I'll write as f prime. And suppose that this f prime has the property that whenever you plug in an x into that f prime, it gives you the slope of the tangent line to that function. So what's the machine that does this? What's the name of the thing where you give a function and the output is another function where this one always evaluates to the slope of the tangent line to that one? Derivative, right? That's the name of this thing. So this is called derivative. Notably, notice that the input is a function. And the output is a function. So the inputs are functions, the outputs are functions. All right. That's neat. The way that we usually write it is with a d. I'll write it like this, d dx. Supposing that the name of the input is x. All right. Good. So what if we reverse the machine, run the machine in the opposite order, and say that, well, suppose that we give a function as input to a machine, and the output is another function, and they have the same property that, well, you give this one as input, and it outputs a function such that whenever you evaluate the input, that's the slope of the tangent line. So it's just like these, but in the other order. So what's the name of this? This is antiderivative. Antiderivative? Well, the way that we denote it, more or less, is like this. So, again, like so, just leaving an open spot there for wherever you're going to put the function. Good. So then notice that in this case, it is still the case that the input is a function. And that the output is a function. Okay, and also, you know, if you don't want to what am I trying to say? Pin yourself down to a variable name, like instead of the variable name being x, maybe you want it to be t or something. Then you could just write this as a single d, you know, little d. And again, to not pin yourself down to a variable name, you could just sort of symbolize this one like so. All right. Now, there's one other concept, and what about this one? Suppose that, again, it's a machine, and we're going to give a function as input, and suppose that in this case, what it does is, conceptually, you could think what it's doing in there is it constructs this shape here, like that. And in this case, it doesn't output that shape. What it does is it outputs output is the area. And specifically, I mean the signed area of the region. Meaning that when it's above the x-axis, area is counted positively, and when below, negatively. Well, what's the name for this machine? Right, that one's called derivative. That one's called antiderivative. What's this one? Just integral. Right? You give a function as input, and then it gives you the area of that region. Okay, specifically, this is fixed here at A, B. So then this one is Gesundheit. This one is integral. And you could symbolize it like so. Something like that. Notably, what kind of thing is the input? Well, it's a function. What kind of thing is the output? A number. Okay, so now, I want to stress that there's two different concepts here, and historically speaking, students are in danger of not realizing the difference between them until it's too late. Notice that antiderivative is a thing, where the input is a function, and what is output is another function. Whereas integral is something where you input a function, and the output is a number. They're not, in that sense, because their outputs are not even the same kind of thing, they don't seem to be that closely related. And they're certainly not the same thing. Antiderivative is certainly not the same thing as integral. But nevertheless, they are intimately connected using the fundamental theorem of calculus. So not the same, but intimately related. Good. Now, because of the close intimate relationship between these two, I want to remind you that the textbook refers to this, instead of calling it antiderivative, it calls it indefinite integral. And this one, the textbook wants to call it a definite integral. All right. Part of the reason to keep it established in your minds as hard as I can, the difference between these, I choose to call these by names that don't sound alike. Antiderivative, integral. In my opinion, as far as teaching is concerned, referring to this one as indefinite integral and this one definite integral would be like coming to the planet and finding, say, giraffes and saying that, because we're aliens and we have long necks, our favorite creature is giraffe. So then there's two kinds of creatures, giraffes and not giraffes. And I think that's not very useful terminology. I think that's about the same here. Okay. That being said, the book calls this thing that we're going to do integration by parts, but really there's actually two different things. There's antidifferentiation by parts, and which is talking about antiderivatives, and there's also integration by parts, which is talking about integrals. All right, so that being said, now antiderivative is running the derivative machine in reverse. The main thing, the thing that makes derivatives so powerful, well, the thing that makes functions so powerful is the fact that they can be composed. And the thing that makes, the main idea, the main result that makes, well, the main result that makes calculus valuable is the name of, is the result that tells how derivative interacts with composition of functions. So what's the name for how derivative interacts with composition? Starts with a C. Chain rule, that one. Chain rule tells what the derivative does with composition of functions. Reversing that, looking at the chain rule but in reverse, the antidifferentiation technique is a variable differential substitution. So substitution is what undoes the chain rule. Now, what by parts does is it undoes something else. So instead of the chain rule and undoing it, we're going to take the product rule and undo it. So what we're doing, in a sense, is that we're going to look at and remind ourselves what the derivative does with product, and then we're going to see how to undo it. Okay. So to remind you, that the derivative of f of x product g of x is given by the product rule, which is where you take the derivative of the first thing, multiply it by the second, put that to the side, then you take the first thing and multiply it by the derivative of the second one. And now that we've done both of those things, how do we combine them? With an add. So we add them. So we do that bit first, just that bit. Then we do just that bit, and we add them up. All right? So then if we write, just for clarity, u is f of x, and v is g of x, then we can rewrite that as the derivative of uv is the derivative of u times v plus u times the derivative of v. And now, as a reminder, the notation, when you write d dx w, where w's whatever, another way to write that is to write dw dx. Okay, so then I'm going to make that change in those positions and say that this is du dx v plus u dv dx. But I'm also going to do that on the left-hand side, right? Because, if I was covering up a w right there, then I'd do exactly that, right? It would be dw dx. But it's going to look a little different. It's going to look like d uv dx. All right. So now, well, remember that these d thingies, they're not numbers and they're not variables. They're actually something else. Depending on which direction you go in math, you can either formalize them as something called a differential or something called a measure, well, something related to a measure anyhow. But we don't really talk about it. Right? But notably, du and dx are not, well, du divided by dx, that symbol is not a fraction. But there's a reason why this continues to be a notation, and that is because in this particular circumstance, you can treat them like fractions. So, well, notice that if we suspend the fact that they aren't fractions and just say, well, what if they were fractions? Notice that if we multiplied both sides by dx, what would happen? All the dx's would cancel. So mult, and I have to write it in scare quotes because otherwise my mathematician training will make me feel queasy. Multiply both sides by dx to get d of uv is du v plus u dv, like so. Now what we're going to do is we're going to solve for that one, okay, for reasons that aren't entirely clear. In fact, we could solve for that one, and the process would work just as well. But you have to make a choice, and historically, the one that all the textbooks do is they solve for that one. So we're just going to stick with that. Doing that, d uv minus du v is u dv. And now I'm going to do one thing, is that product commutes. So I'm going to write this as d uv minus v du is u dv. So all I did was commute that. And now equal is reflexive, so I'm going to switch the sides. U dv is d uv minus v du. And now I'm going to anti-differentiate both sides. So anti-differentiate, whoops. Yeah, I had it right. Antiderivative of u dv. And then remember that the antiderivative is additive, which means that it distributes across that subtraction, so that it looks like antiderivative of d uv minus antiderivative of v du, because it's additive. And now here's the thing, is that that's the antiderivative of the differential of uv. Which means that, well, wouldn't it be nice, wouldn't it be a gift if one of these were the, you know, if exactly that was an exam exercise, right? Well, what's the answer? What, the antiderivative of dw is w, right? You know, plus a constant. Well, so what's the antiderivative of d uv? uv. Right? So whatever it is I'm covering up, when you do antiderivative of differential of that, it's that. That's what you get back. So this will be antiderivative of u dv is uv minus antiderivative of v du. There it is. That's a formula. So I'm going to write it on the next page because I have to write its counterpart also. Another formula you have to memorize. So therefore, here's a new formula. Antiderivative of u dv is uv minus antiderivative of v du. This formula is called antidifferentiation by parts. All right. Then there's a corresponding integral. So if we take exactly that and write u dv, but now we're going to say a to b. And remember that u is really a function of x, and so is v. So somehow I have to take this, I've got to finish this, uv like so. So we're just going to finish the formula, and that'll be the last thing that we do. So now here's the thing, is that with antidifferentiation, what kind of output does antidifferentiation give? A function, right? When you calculate the antiderivative of a function, the answer is another function. When you calculate the integral of a function, what kind of thing do you get? A number, right? So specifically, we've got to amend the right-hand side so that we get a number and the right number. So fixing this one is easy enough. What do you think we need to do to this to make it right? Because right now, this would be saying a function, a to b. So that's good. But remember, u is f of x and v is g of x. So at the present time, this is a function. So now it's still not right because we need all these things to be numbers. We need this to be a number, that to be a number, that to be a number. So what do we do with this? Well, let's think about it for a second. Remember that integral, what it does is it takes the shape and cuts it into rectangles. And what it does is it evaluates the little f at infinitely many places, right? And the fundamental theorem is saying that, in fact, you don't have to evaluate it infinitely many places. How many places do you need to evaluate? 2 places. But you need to evaluate a different function. You need to evaluate the antiderivative. So that's what we need to do here, is we need to evaluate this at the boundary. Now it's right. So this one is integration by parts. Yeah. I mean, they're obviously related, right? All the u's and the dv's are in the same places. But this one, the kind of thing that we're talking about is a number, whereas in this case, the kind of thing we're talking about is a function. Okay, so that's all the time that we have for today, and doing exercises with this is what we'll talk about on Thursday. Did you have a question?
So is this much different? I mean, is it kind of like what we've been doing with the precursor to this? Because it was more like what we've been doing for the initial series, or no? So I'm saying, it's almost like...
You can think of it like this. You know how when we're doing antiderivatives, and then I say, I always go through the same thing. I say, is this one of the blessed 3 antiderivatives that we know? And then usually it's no. And then I say, well, can we do something algebraic to turn it into something that we know? And then usually, recently, the answer's been no. And then, then I ask, well, what's the next thing? And then y'all say, a variable differential substitution. And then we try it. Okay. That variable differential substitution is step 3 in the Riesz algorithm, in the Riesz procedure. That's what we're doing.
Okay.
This is step 4. If you can't figure out how to do a substitution, then you try this technique.
Okay, so kind of like when we're looking at it and the substitution wasn't going to work, then we're using this now.
Then we're going to try this.
Okay.
I'm assuming we're doing the West Business on Thursday.
Yeah, we're going to do that on Thursday. Sorry.